experiment work. So it's going to be a lot of fun. And this is just one of many Dark Matter Day events taking place around the world. We're one of the first ones to host an event. So I'd like to start by introducing our moderator, Gavin Cox. Gavin is an experiment support scientist at SURF, and he is working on the LUX-ZEPLIN dark matter experiment. He has a Master of Physics degree from Penn State and has been working with LZ for 5 years. So I'm going to turn over the mic finally to Gavin. Thank you, Gavin.
Thank you, Constance. I'd like to welcome you all to Dark Matter Day here in Leeds, South Dakota. So let me start off by introducing our panel. So first we have Pedro Mercado. He is a scientist at Fermilab. He's a theoretical physicist working primarily in neutrino physics, as well as dark matter and Higgs physics. He's a member of DUNE and the SBND experiments. His work is focused primarily on phenomenology, which is the interface between theory and experiment. We also have Professor Chamkar Garg. He is an astroparticle physicist leading the research at University College London to experimentally detect dark matter in our galaxy. Chamkar is the spokesperson for the International LZ Collaboration, which is operating the world's most sensitive dark matter experiment ever constructed. And he also collaborates widely outside of fundamental physics within the arts, neuroscience, and earth sciences. And here in the room with me, we have Charles Maupin. He is a mechanical engineer here at the Sanford Underground Research Facility. His focus is to support world-leading science experiments. Previously, he worked in reliability engineering and automated equipment design. He holds a Bachelor of Science in Mechanical Engineering from the South Dakota School of Mines and Technology. All right, so the main purpose of this panel is to discuss how our knowledge of physics develops, from concept to discovery. So very often, the theory describing some physical observation will precede its discovery by years, often decades. So this large gap between theory and experiment would lead one to believe that these two areas of physics have very little influence on one another. So today, we'll spend time discussing how large this separation actually is. And then we'll also go one step further and discuss the relationship between developing an experiment that could exist and actually creating a real-life functioning detector. Because in doing so, practicalities often present problems with the construction of the detector and ensuring that you're producing quality results. All right, so to begin, I'm going to ask each of our panelists to describe what your field has brought to the current state of dark matter. So let's start at the top with theory, and then on to experiment, and then finally, engineering. All right, so Pedro, let's go to the very beginning. Dark matter was introduced as a concept to explain the gravitational excess observed in galaxies and galactic clusters. So it's then the responsibility of theorists to develop ideas that are able to explain this gravitational excess. So how does one go about developing a novel concept for dark matter that's still within the bounds of the physics that's already been established? Thank you, Pedro. All right. So now let's turn to Chom to find out how we would go about testing an idea that we've come up to explain dark matter. So given that we have a model for dark matter that can explain these observations, how do experimentalists determine how they'll design an experiment to test this model?
Yeah, so in the case of dark matter, the sort of favoured theory for quite some time, because of the sort of the naturalness arguments that Pedro is mentioning here, it has been the weakly interacting massive particle. So we'll call it the WIMP for short, and we can break it down. Right? The massive particle part is more easily understandable, at least to me, in the sense that we're seeing something happening out there in the cosmos. Things are moving around in orbits, with velocities that are way too fast. It's as if something's holding them in. It's as if there's some kind of glue, there's some kind of matter, which is where something with mass, right? That's the only way we can explain it. There's something gravitational there. But the weakly interacting part is an interesting bit, right? Because it doesn't have to have a weak interaction. Dark matter may not interact at all. In which case you can't ever detect it. Well, not readily. I mean, maybe in a few hundred years there'll be some grand ideas like build a galaxy with dark matter and one without. But for now, we postulate, right? So theorists sort of hand us these theories. One of them that has had a lot of traction has been this one called the WIMP. And I come to that weakly interacting part, the WI in WIMP. I'm going to talk about what's called the WIMP miracle. And maybe in a few, after LZ and maybe probably the next iteration, maybe the WIMP miracle is dead and it's no longer motivated. But what is it? Just very quickly, it's to say that if we look at our models of the standard model of particle physics, and we look at what everything is made of, then it's clear that there's more out there that isn't explained by this model, and we call these beyond the standard model theories. And when you try and sort of construct many of these beyond the standard model theories that are trying to explain, some of the known issues that we have. Why is there more matter than antimatter? Why are neutrinos oscillating? All these kind of things. But much more as well, sort of stability of the Higgs and things like that. Then sometimes, I think often, a lot of these theories will sort of have this sort of, I'm going to call it a throwaway particle. Like, okay, we've solved our issue here, but there's this kind of relic particle that's left over. And all right, there's a particle that was sort of born in the Big Bang. There's lots of them about, and they would annihilate. If they were around, in the early Big Bang, there'd be so many of them that they'd be co-annihilating, and they're just sort of vanishing into energy or other forms of matter, until eventually, as the universe is sort of expanding and cooling, the number of dark matter particles drops, and then it sort of freezes out. So now dark matter particles are no longer in the early universe. They bump into each other, they annihilate, and they're gone. And the number of them, reduces. But at some point, the universe is so big that they never meet each other anymore. And so now the amount of dark matter that you've got there is what you've got there. And you can look at the theories and you say, all right, okay, well, if this particle would have a weak interaction, it would occasionally interact with one of the weak nuclear forces. If it did that, it would annihilate. There'd be maybe so much of it left around now, and it'd have this sort of mass. And then astronomers look out to the cosmos and say, what we could do with a particle that's born in the Big Bang that would have something like a weak interaction, that would have this sort of mass, and it fit the bill really nicely. And that's what's called the WIMP miracle. So, all right, now we come to the experimentalist part of it, and we say, all right, I want to know what dark matter is. Seems like WIMPs is the way to go. That's sort of it's the best first bet, if you like. Before we have to start getting very nuanced. Occam's razor has often, has told us that the simplest ones tend to be, more right. So the weak interaction in that WIMP name means that occasionally a dark matter particle, if it's a WIMP, will interact with the nucleus of an atom. So I could build a WIMP detector like this, right? I could hold my finger up, and if I held it there for about, 20,000 years, something like that, a dark matter particle at the moment, if dark matter is WIMPs, then we've got something like a few 100,000 of them going through my finger every second at about 500,000 miles an hour. And if one were to interact, because it has a weak interaction, then it would hit a single nucleus of a single atom in my finger and move that nucleus by 1,000th of a hair's width. So that's what we're trying to detect. right? Something that never happens, or very rarely happens, and if it does, it's going to give you the most stupidly feeble energy. So great, sounds like fun. So the experimentalists get involved. It's like, well, this sounds bonkers. Let's try. So what you want to do then is essentially build you want to make the detector large, so you want as many dark matter particles streaming through this detector as possible, with the hope of actually, interacting. And then you want to make it highly sensitive, so that if anything does interact, if you do get a nucleus moving 1,000th of a hair's width, we spot it, and we spot it easily. And that's crucial. So we want to have mass, we want to have sensitivity, and then we need discrimination. We've got to be able to tell that if something does come and hit the nucleus, as opposed to an electron around, an atom, a gamma ray, just a boring standard model particle. We love them really, but in this scenario, they're boring. We want to be able to tell them apart from what's hitting the nucleus from the WIMP. And so that's the fourth component, discrimination. So you can build, you can try various technologies. You can try your finger, but it'll take a while. Or you could build maybe a 7-ton. You can put 7 tons of liquid xenon into a highly reflective cylinder, instrument it with light sensors that are able to pick out a single photon. Right? Think about that, a single photon of light, and also be able to detect a single electron moving through the xenon and generating light as well. If you do that, then you've ticked all of those conditions. And we've been working towards that for a couple of decades, really. In the last decade, this technology's really matured. But now we're into sort of fun times where it runs, it's built well, it operates reliably, and we can really go after dark matter. And this is years of R&D, right, to get to this point. The first detectors were nothing like this, much smaller, broke all the time, cobbled together with gaffer tape and so forth. But now we've got great shiny instruments that I'm sure Charles will tell you about.
Oh, well, thank you, Chom. So at this point, we now have a model for dark matter from the theorists and an experiment that is able to test this type of model. So at this point, Charles, surely everything just goes to plan and you build the detector? Super easy, right? So how would you go about meeting experiment requirements and, balancing practicalities along the way?
I mean, I guess I will say it's when it's planned. John talked about we have a detector, it's operating, it's been operating fairly reliably for, a couple years now? So it went as planned. But what has went into that is as Chom talked about, years and years of planning. So when you look at the course of LZ, really the development and the planning for it started when its predecessors were just getting started and were not even through their life yet. So everything went to plan, but that's not to say that wasn't without great effort. The planning took many years. Everybody asked me about when I first started at SURF, and I never went underground. I was basically stuck in my office for 3.5 years doing the design of LZ. When you look at the design of LZ, we designed everything on a computer, made sure all the parts would fit together, and then we started building stuff. And we started manufacturing it. Some of it was assembled on the surface and was taken down the shaft. When you look at these experiments, especially your underground experiments, you're actually building a ship in a bottle, and the neck of that bottle is 1 mile underground, and the experiment itself wouldn't fit in this room. So it's a very complex problem, but I will say everything went as planned. Sometimes we had to kind of rewrite the plan as we went and take everybody's input on that to make sure that we got to the outcome, the safe outcome, but it went as planned.
Well, thank you, Charles. So we now have our stepping stones going from theory to experiment to construction. Now, with theory at the very beginning of this process, it seems like it'd be the most isolated of the three. So, Pedro, in what ways does theory rely on the results of experiments?
Well, actually, we might be the starting point, but this is more like a cycle, actually. If you think about it, let's take the WIMP miracle, as we were discussing here now. for the WIMP miracle to work, for WIMPs to be dark matter, it needs to talk to the standard model, it needs to interact with particles of the universe that we know, but we don't know exactly to which particle is interacting and how much. So if tomorrow you come up with an experimental result that says, look, I have my big detector full of xenon, for example, and I am not seeing this dark matter interacting here. So now I go back to my theory and say, wait. Does it mean that WIMPs are dead? Or does it mean that we actually need to be a little bit more careful because maybe there is a stronger coupling to this particle than that one, and this, and that? And as you get experimental results from different places, you're kind of cornering your theoretical ideas more and more. And hopefully some of them you can actually just refute them, right? This is science. You can actually say, hopefully you can actually say, oh, this is not it. That is not it. And eventually we'll get to the point where maybe we find what dark matter is. So it's more of a cycle than of a 1, 2, 3 line. And then there is another point, which is we're talking about WIMPs and we're talking about experiments of these direct detection experiments, but there are new technologies and new techniques to probe dark matter. So if you tell me that now you can build, say, a quantum device that can have a single photon resonating in a cavity, then maybe that is not good for WIMPs, but it could be good for some other dark matter particle, other dark matter hypothesis, like what we call axioms. So if you give me novel techniques, I might think about what new theories I can test with these novel techniques. And then you rinse and repeat that until you find dark matter, I guess.
That does make sense. And going further into the results of an experiment, Pedro, so you mentioned how, as of right now, we're still probing into WIMP parameter space and still not finding anything. But for theory, in your opinion, does a null result where you don't find anything or a discovery typically have a bigger impact on theory? And could you give an example?
So discovery would be like magnificent, right? But of course, we are still looking for it. As we are getting no results, they do have important impacts on theory. For example, if I just close my eyes and I write the first theoretical model of dark matter one can think about, which is WIMPs, the most simple realizations in several aspects do not really work. So now I need to be a little bit more careful about that. So this is how experimental results do impact the theoretical ideas. Or even, if we go one step further, there are alternatives for dark matter, which are called modified Newtonian dynamics, or MOND for short. And this is essentially saying that gravity doesn't work the way we think it works. And there are observations, this is a very interesting theory actually, but there are observations that are simply not consistent with it. So there are observations of, for example, clusters of galaxies, like these gigantic groups of galaxies crossing each other. And if this is just a modification of gravity, you should just see two blobs of matter, but you kind of see actually four. Matter from one group of galaxy, matter from the other one, and they cross each other so they have some specific shape. But there is also, you can also infer the presence of dark matter from the two clusters by looking at how the presence of dark matter changes how light propagates, because it generates gravity, no? So by looking at these things, you say, it really doesn't look like this is a modification of gravity. It really looks like a new particle. So experimental results can have deep impact on theory, and they have been, let's say, killing, beautiful ideas, which is good, right? It's very good that experiments can kill beautiful ideas. We just hope that one of these ideas sticks and we get to discover them.
All right, thank you, Pedro. So let's turn over to Cham then. For LZ, as you were mentioning, the theory of WIMPs is the primary dark matter candidate, which was the driving factor in its design. What were some of the ways that the detector was designed to optimize the chance of detecting WIMPs?
I mean, it's optimized for WIMPs, sort of. I mean, it is, but we can simplify it even more, really. It's sort of optimized just to be as sensitive as possible to any interaction. And so that fits the bill for WIMPs. And so really, some of the things we have to care about are, for example, light yield. If a dark matter particle comes in and you give a little kick to a nucleus, that nucleus recools and you get some photons of light, but just a few. And you can imagine if your detector's quite small, that's fine, you're going to collect that light. But if your detector's getting larger and larger and larger, now you've got 7 tons of this stuff and photons are bouncing around, you might start to lose some of these. So you want to be very careful that you are able to maintain the lowest energy sensitivity, a single photon and a single electron. And then to make sure that we can see that signal against all the background is another part of another part of the game, which again isn't necessarily just for WIMPs. It's for any rare event search. So pretty much all of our models of dark matter, imply that it's going to interact rarely, or we would have noticed it by now. And so for that to work, you have to construct the experiment not just with incredible precision and design, but the parts that go into the actual realization of the design that Charles and the engineers are working on. Each one of them has to be screened and assayed to check what's in it. It's almost like before I can drink from this mug, I've got to check the level of uranium, thorium, potassium, coal, all sorts of stuff. I've got to do a whole ton of analysis that takes me a month per component, per individual item. And we screened something like 1,200 items using all kinds of different techniques. And you say, well, what were these techniques we used? Well, some of those we had to make up because there aren't, there's not off-the-shelf industry stuff that we can just use to do what we need to do to select these materials. So the point is that, we took a long time making sure that everything that goes into that experiment is giving us hardly any background. And so that's kind of one of the primary requirements. It's got to be low background, as in all the other stuff that isn't WIMPs has to be absolutely at an incredibly low level. And we've got to maintain low energy sensitivity. And then, as I was saying, it's got to be big and all that kind of stuff. You've got to be able to tell the difference between this and that. But the quietness, in terms of the radio quietness, the center of LZ, in terms of radiation and background that would give it, that would maybe mimic a WIMP signal or anything like that, it's the cleanest place on the planet. When I say on the planet, I mean in the planet. Anywhere in or on the planet. If you want to look for new physics, just stuff happening that you would never be able to spot in busy environments, like a collider or something like that, very high energies and things, then this is a place to do it. It's designed to be able to spot the tiniest signals, the tiniest perturbation in that xenon from the rarest of signals. So, and if you get 2 tiny little events over the course of 5 years, no problem. We'll spot that. I say. We're designed to spot that.
So like you were saying, it's designed to be an extraordinarily sensitive detector. So are there any other theories that LZ could prove or disprove during the course of its run, besides looking at WIMPs?
Yeah, absolutely. I mean, for a long time, when we were, before, we would we would highlight the sensitivity, or we'd sort of present the sensitivity of this planned experiment. We say, look, we're going to get down to here. It's going to be great. And then, sometimes funders or somebody say, but what's there? Put some theory blobs on there as well, so we know what you're targeting. And so the WIMPs are very useful for that, right? We can show, all right, this is where we're going with the WIMPs, and it's a very well understood sort of paradigm now. Although as we push them further and further, they've got to get more and more and more nuanced, right? As Pedro was saying, these kind of, you've got to tie up all these little loose ends, and the WIMP miracle gets less and less miraculous. But even so, having a detector like this, we can go after some of the axions that you heard about earlier. They come in different sort of disguises, guises, brands, whatever you like. And so some of them we could pick off even with LZ using a funky sort of hypothesized effect called the axioelectric effect. It's sort of analogous to the photoelectric effect. And then there's other forms of sort of, more particulate dark matter in the sense of WIMPs that can come and give you sort of, recoils and things. So there's things like asymmetric dark matter and so forth. So what I'm trying to get at here is that the dark matter problem can be solved by some 60 orders of magnitude in mass of different candidates, from black holes to tiny subatomic particles. When we look at just that sliver that is the sort of subatomic particles, within a range that we can catch, there's tens of different of models that we can go after right there. And it used to be that with the smaller detectors, we could only do WIMPs. But now as you get larger and larger and larger, the xenon at sort of at the edge of the detector itself is shielding, it's stopping radiation getting to the very core of the detector. That's why I say it's the most sensitive and quietest place in or on Earth. And so as that happens, as you get larger and larger and larger, the backgrounds are getting lower and lower and lower. So your job's getting easier and easier, and you're able to then expose more and more different types of signals and different types of physics. So there's a whole bunch of dark matter sort of physics, dark sector physics, but then there's beyond the standard model physics as well. You can do things like the neutrino magnetic moment. You can measure, we surely must measure a boron 8 signal. So this is a neutrino signal that comes from the neutrinos that come from the sun, but they do something quite special. They come and they interact with the nucleus, much like a WIMP would. And this is called coherent elastic neutrino nucleus scattering, and it's never been observed astrophysically. We've seen it in the lab. Once one experiment has kind of measured this, a reactor actually in the lab, but on Earth. But we've never seen it from an astrophysical source. We've never seen it in a flavor blind processes. There's sort of lots of fun physics that you can glean if you measure it the way we want to do it. And then there's neutrinos double beta decay, which is itself a bigger prize as dark matter is. I'd say, it's a detection of two sort of beta decays with no neutrinos, because they've kind of annihilated, will tell us much about matter-antimatter asymmetry, and also start telling us about the neutrino mass in absolute terms, which is very tricky to do otherwise. And so these neutrinos double beta decay experiments in particular, they're pretty much dark matter detectors, or they would say that our dark matter detectors are neutrinos double beta decay detectors. We're just we're targeting different energy regions. So dark matter happens at the low energy region, and the neutrinos double beta decay signature happens much higher. But when as I say, once you start getting so large that even your high energy backgrounds are just sort of not entering the core of your detector, you can search for that as well. So it ends up becoming a multi-purpose detector, or the way we used to phrase these sort of 10, 15 years ago is a broadband. It's a broadband search for new physics. We're building an incredibly sensitive device, and we're sort of putting it out there saying, all right, well, this could see the dark matter models that these theorists like. It can't see those ones, but it could see this, could see that, could do neutrinos double beta decay, and so forth. So there are some that are sort of sure bets, like the astrophysical signal from the sun. Others are, shots in the dark matter, like WIMPs. Neutrinos double beta decay could well be. There's good evidence with that. So there's some sort of very exciting bread and butter type stuff that we hope should be there, and then there's all the kind of open stuff, but it goes well beyond WIMPs. In fact, just today, in the LZ collaboration, I finished reviewing, sort of within collaboration review, there's a paper that's going after a specific type of dark matter, not the standard WIMPs. And I just finished the collaboration review and was putting my laptop down, and another ping came in from another collaborator saying, and now we've completed this, here's another paper, collaboration start reviewing this. And that's another completely different model from the standard WIMPs.
Well, thank you, Chom. It's very exciting how many different areas of physics that LZ has the potential to probe during this time.
Yeah.
So we'll move over to Charles and talk about the construction of LZ. So when you're given the specific design of the experiment and their goals, what are some of the challenges that you experienced during LZ's construction? And how would that differ from a more non-scientific engineering project?
Well, I have to say one of the main differences, because when you look at coming from automation and automated equipment, we used a lot of the same stuff. We were able to pull back into the old catalogs, you grab the parts. One of the main differences that I'll say, and Chami did a very good lead into this, is the radio purity side of it. So when you look at a lot of what we did was more conventional and common engineering. You're trying to design parts to where they don't fail. So if you've got something that's got pressure inside of it, you want to make sure it doesn't blow up. Stuff like that. That's the stuff that, as an engineer, you go to college and they explain to it, and you go through all the theory and how to design everything. The part of this environment that isn't covered is now all of a sudden you have to meet all of those specifications, all of those requirements, but you have to make it and select materials and design it in such a way that it won't contaminate and increase the background of the detector. So when we were designing things, a lot of that stuff was either in the detector itself or very close to the detector. As Cham talked about, we had to screen all of our materials. One that kind of sticks out in my mind was it was a challenging problem just because of what it was. It was a heater that was going against one of the elements of the detector that actually keeps the detector cool. So it had to be able to basically survive at minus 320 degrees Fahrenheit. That's pretty cold. So you typically don't think of maybe a heater needing to get that cold, but in this case it did. So it needed to be able to survive the extreme temperatures. It also needed to survive in a vacuum chamber, which we use vacuum to insulate the detector, but vacuum, you can literally pump solid things away. So in the course of keeping our detector cold, it's possible that we would completely remove this heater and destroy this heater just by vacuum pumping on it. So you had that challenge. So you're trying to go out to a vendor to find this one part that's a heater that can go down to minus 320 degrees. It'll fit in the form factor we need. It gives us the amount of heat we need. But then, oh, by the way, you got to take this heater that maybe there's only one of them, one company that makes it in the world that'll work, and then you have to make sure that it's not going to contaminate the detector. So we were fortunate to find this heater. We bought them. And so then we sent it off for background screening. And on Christmas Eve, a physicist thought it was kind of funny to send the results of the assay. It actually came back so it was too hot. So we actually thought for a split second that we had to go all the way back to the beginning. And that actually does happen. You would get to the end game, you would find something, and all of a sudden that material would not work for your application. So you'd start all back. And so there's that challenge of trying to meld the conventional engineering with, you've got to create a very ultra low background detector, and because of that, your material selection is very key. So when you look at LZ, we had the world's purest titanium. The detector itself was actually made out of large billets or large chunks of this titanium that was the world's purest. So you had the design challenges of building this big vessel to house everything, make sure that it was small enough to go down the shaft, but you had to use this very exotic material and find the right manufacturers that could actually work with it. So that's one of the biggest challenges of working within this environment, and that's very different than working out in other industries. I doubt you would ever find this in conventional industry.
Well, every step of the way seems like an interesting place to be working in. So this is going to be a question for everyone involved. So specifically for Pedro and Cham, what made you choose theory over experiment, or vice versa? And then similarly for Charles, what convinced you to continue working as an engineer in a scientific environment rather than an industrial one? So we'll start with Pedro on this one.
So I think for me, choosing theory was very natural. I remember the first time I saw Newton's laws, I just could not understand how a handful of laws can describe from, pebbles to planets. it's mind blowing, right? You tell me that the game only has like 3 or 4 rules, and you explain everything you see. It can't be right. So the first time I saw that, I was like, wow. I mean, there is something real deep about this. And then afterward, I saw Einstein's theory, which is even worse. It's like you look at that, there's again a handful of rules, and it predicts the most weird things you could ever imagine, right? That, for instance, the twin paradox, no? When 2 twins, one travels at the speed of light, comes back, he's younger than the other one, and so on and so forth. And everything comes from a handful of rules and math, right? That's mathematics. Quantum mechanics, it's another mind-blowing area of physics. So I think for me, every time I would see something like that, I would just try to understand more and more, and like learning these things have been incredibly rewarding for me. And the final theory, let's say the theory of everything that we have as of right now, which is not string theory, because string theory doesn't explain experimental data. The theory of everything that we have is quantum field theory, which is what the mathematics that allows you to write the standard model. So basically, again, it's a handful of principles. You correlate mathematical symmetries with forces of nature. You tell this to somebody in the street, they'll look at you and say, you're crazy, you shouldn't go to a hospital or something. But it works. It describes data, and it doesn't describe data at the 10% level. It describes data at the 10 to the minus 8, 10 to the minus 10 level. It's insanely good. So these things for me are puzzles that I can just not stop looking at them. And I guess this makes me a theorist.
And we can move on to Cham then.
Yeah, I think I lucked into experimental physics more than anything. I think I started with the idea, not really understanding the differentiation really between theory and an experimentalist. It was more just wanting to learn and learn and learn, and eventually got to the point where it's like, all right, so dark matter, cool. Learned about this a few years ago at school, and now I'm here at university, and now someone's going to tell me what it is and say, no, we have no idea what it is. This is where we set, and yeah, and then it's the old, in 1933, Fritz Zwicky, and that's it. And we go on and on and on. And it's like, so wait, nobody knows? No, surely in my final year, someone will tell me, right? And it's like, no, nobody knows. And so then I think in me, it's just that probably a deep mistrust or cynicism. It's like, all right, well, shouldn't we get on that? Should we not, like, try and figure out what this is? We've got some good theories. And then I think it's just luck. Yeah, I remember I was at a seminar where a chap called Nigel Smith was giving a seminar about dark matter. And I was like, all right, what was the experimental side of it? And it seemed challenging. It scared me. It was just daunting. It's like, wow, where would you even begin? Like, what is this? And so as much as that scared me, that seemed to be what was sort of pulling me in. It had its own gravitational well. And, my lack of intelligence sort of prohibits me from being a theorist as well. So there's that.
I don't know about that.
All right, Charles.
So I guess what kind of what has kept me and what drives me to keep working in science is kind of what drew me to starting to work in science as an engineer in the first place, and that's the challenge. So when I was reading through the job posting, I was like, I know nothing about this, but it intrigued me because I knew it would be challenging. And so when I got the position, I just kind of started relating things back to what I had done before, and it was definitely more challenging than what I had done before, but I'm a person that's what drives me. So if I can't figure the problem out, you just keep pushing on it until you get one little chunk, you get a little breakthrough, and then you just start that, and it's kind of like a snowball rolling downhill, and pretty soon you're able to get to the bottom and get to the outcome, and it's not always a smooth or easy road getting there, but But the challenge is what drove me to the position and what has kept me here, so.
So we'll have one more question for each of our panelists. So I'm going to turn over to Pedro and Cham for this next one. Looking ahead to the future of dark matter, what excites you the most? Whether that's a new theory looking to be tested or a new experiment looking to test an existing theory?
So to me, I think that it's the interplay between these two things. I'm a bit biased because I love to work I am a theorist, but I love to work with experimentalists. I don't see a point of doing theory that cannot be proved at experiments. So I think the interplay between novel techniques, large experiments, new telescopes, new observational data with theoretical ideas, it's mind-blowing right now. For instance, we just observed gravitational waves, which was predicted by Einstein in 1910 or so, right? 100 years ago. And these are basically, so the same way that if I throw a rock on a pool, I generate waves, because matter deforms space-time. That's how we understand gravity. If I get matter, let's say 2 black holes, and let them spin around each other, this generates waves in space. So these are gravitational waves. Super hard to detect. But we did. And now with that in hand, what do we do? What new theories can we look for? And of course, with experiments like LZ, plus, let's say, gravitational waves, plus, let's say, the Dune experiment, and data from telescopes, how can we combine all these things to keep not only pushing the dark matter space, right, but also to come up with novel ideas of how to leverage all this data, all this rich environment. So I think the future is very bright for dark matter. It's a very exciting intellectual environment, and I am convinced that we will find dark matter soon. I'll just not say what soon means, but soon.
Thanks, Pedro. And you, Cham?
Much of my answer is just copying Pedro. I think so. For me, I'm also excited by even though they've come, the gravitational wave discovery was 2015, 26? I can't even remember. Sometime. We had the Higgs 2012, and so some of these they don't necessarily all come in at the same time, but they do come in. Right, and we're starting to probe the universe in different ways. Like the gravitational waves means that we can now, we can see stuff without electromagnetism for the first time. It's incredible. In principle, you had a sensitive enough gravitational wave detector, you can spot aliens sipping cups of tea, right, from wherever you are. It's bonkers stuff, gravitational waves. The more you really start thinking about it. But then when you start coupling that to other discoveries, other things that we know is there, again, me being sort of, cynical and distrustful of everything, but it's, something, if you take the Higgs field, this was a discovery of a scalar field. It's there, we've measured it, we've awarded prizes for it. And we posit that early on in the universe went through this period of rapid expansion called inflation, where it'd be great to have a scalar field doing this thing. And it's like, well, we've never spotted one. We have now, right? Is it the same thing? Probably not. But how are they coupling? What's the inflationary field doing at the time of the Higgs field? Does that leave remnants in space? Does that leave something that gravitational wave detectors could probe? Does that in turn tell us something about space-time? Another one for me that I'm hopeful about is sort of, the getting a bit deeper into our understanding of the universe's process, right? Because we've got our best theories are quantum field theory, and that's, all of them. We have gravity and then we've got quantum field theory. But what really stands under them? How are we going to end up with the appearance of a universe where stuff moves in it? That's not what's going on, right? So, but that's what it's going to look like to us. So as we get deeper and deeper into that I think will get fun. And then there's sort of looking out into space and just seeing the motions of bodies out there. So looking at satellite galaxies and things like that can start to tell you whether it's, it can start distinguishing between types of dark matter. Is it warm dark matter? Is it cold dark matter? Is it this? Is that? And as we get more and more precision, as we look out into space, I mean, for me, for so long, I was, sort of, blown away by Hubble. And now you look at, James Webb Space Telescope and Gaia and all, the new instruments that are going up there, they're phenomenal. And so there's so much that I think we're going to learn as all of this starts to come in. And I think as we start to piece it together, I really like the way Pedro put it. As you put this stuff together, maybe you start unraveling or unpicking the dark matter problem in a completely different way. Maybe it's not anything like we think, but if it is, then all these other clues will start helping us. And then just finally, very quickly, there's also the technological sort of advances. Pedro mentioned quantum sensors, for example, go after axions. There's other types of quantum sensors that are are sort of atomic and molecular physicists have built these wonderful technological devices, and then along come some sort of fundamental physicists and dark matter hunters and say, well, that's pretty cool. Can I play with that? And let's collaborate. And so then you start opening up all kinds of different avenues for incredibly exquisite sensing. And when you think about just sensing, even outside of dark matter, outside of particle physics, that's pretty incredible, right? If you think about neuroscience and things like that, we're pushing boundaries that I don't think we have any idea where they're going to end up. Sort of moving into day-to-day life. But it's exciting either way. There's just so much to learn. There's so much that we don't know. It's always exciting.
Thank you, Chom. And I'd agree, the physics community is at a very exciting time in history right now. Looking forward to see what it comes out with. So for Charles, working on LZ has obviously made you work under an entirely new set of constraints. So will this experience be beneficial for future experiments? And if so, in what ways?
Yes, very much so. I mean, looking at, say, Dune that's coming here, even from the standpoint of everything will come in on the surface and it will need to go underground. I mean, LZ learned a lot of lessons about how to handle equipment, how to handle sensitive equipment, and that can be directly applied to getting things underground. Now, obviously, the pieces are different, but you can handle things the same. From more of the experiment and the assembly underground, I mean, we learned a lot about our cryogenic system, insulation, so forth. A lot of that can be applied. A lot of your gas handling systems, a lot of the technology there. There's different purity standards as far as for argon versus xenon. But you can still take a lot of those principles and the lessons learned and apply to larger experiments. You can even take it, I mean, that's the case of Dune, which will be housed here at the Sanford Underground Research Facility. But there's already discussions about Gen 3. And there's individuals and groups that are working on Gen 3. And when you look at that, virtually everything that was learned during LZ can be taken and moved into that. Now, obviously, there's some differences, and that's where a lot of the challenge comes in is larger experiment takes larger pieces. So to try to get them underground, you're very much constrained by the size of your shaft. So you're having to look at very different manufacturing techniques for how you can actually assemble things and get it built. And so, but kind of basically just taking the lesson learned that you always need to learn and develop yourself, that's a big one, because you're going to have to, in some respects, reinvent the wheel.
All right, thank you, Charles. And that will conclude our discussion from theory to experiment. So let's have a round of applause for our panelists. So I'd like to open up the floor to the public. If you have any questions you'd like to ask the panel, I'll come around, bring the mic to you.
All right, we both have questions, but Pedro, I heard you mentioned string theory, And I was just wondering, what's the relationship, or if there is a relationship at all, between string theory and dark matter?
So, as far as you know, there might be relations, but they are not very direct. I mean, the main challenge of string theory is to predict what we have observed in the universe, but the theory is actually very complicated, and you know, making this prediction is actually not very easy. So, what I would say is that there are some kind of maybe indications here and there that, you know, maybe like a common thing that you can find in string theory are like scalar fields, like the one that Chan mentioned it before, and maybe this could be dark matter, but the predictions are very fuzzy in some way. It's not like you know, there's nothing very sharp on this prediction as far as I know.
Thank you.
Hi, so yeah, Charles kind of talked about challenges on building it right away, and then Pedro mentioned how everything's not so linear between theory, experiment, and engineering, and it's more of a cycle. I just kind of want to know, how often do you have to make adjustments, and how difficult are these adjustments on all of your guys' sides?
I guess from the engineering side, we made changes frequently, but a lot of it was on the day-to-day stuff. And we would, in the early design phases, I remember going to a collaboration meeting, and basically one statement made a change that negated the last 6 months of work. And so it kind of depends on what phase you're at. In the early, when everything is changing and we're trying to get everything hammered down, large changes could be on a daily basis. And as you get closer to the end, your changes would become less frequent and often smaller. I mean, when we were assembling things underground, we would make day-to-day decisions, but it was maybe we route this cable over here as opposed to over here. Or we would add some extra reinforcement here to make sure that something didn't come loose. So it was very minor changes, but they were frequent. And some days everything would go as planned, and we wouldn't make any changes at all from our original plan. So it kind of very much depended on where you were at in the scale of the changes, and then the frequency of it.
Awesome, thank you.
Charles, what kind of obstacles or situations did you run into getting your experiments from the surface to underground?
So some of them, we would have to get creative of how to get them underground. And fortunately, Ricky, you know, because you helped us get a lot of it underground. We would very much rely on the team, and we tried our best to get things to fit in the cage, but not everything would fit in the cage. So then, all of a sudden, now it would have to be underslung. So the challenge in that was just your work planning. And a lot of this equipment was very sensitive, so you had to make sure that you weren't damaging it on the way down. We like to think everything fit and it just went down, but we did have things that scraped. I mean, we sized everything so it would just barely fit down, because that's, in particular, the detector. We didn't damage anything going down, everything functioned, but there was definitely times we were sweating to make sure that it went down. Today is a prime example of one of the challenges that we faced. So I was just talking earlier that whenever we would schedule a shipment of xenon, with the exception of about 5 packs that came in August, we would always get a snowstorm that would mean the truck would get stuck somewhere. When we actually went to ship the detector underground, we buttoned it up and got it ready to make its trip underground, and it started snowing. We got 2 feet of snow that night, and we actually had to delay it going down by a day. And so that's some of the challenges. I mean, the weather in this area is it can be good one day and terrible the next. Yeah, so there was a lot of challenges, but I will say everything got underground, everything got down and functioned, and it worked out.
All right, let's have one more round of applause, or we have time for one more question then.
Can you give us an idea of the status of Dune, where it's at, where the whole project is? You mentioned it a couple of times, and what's going on with it?
I'm perhaps not the best person, but I can kind of give, or somebody else, but it is progressing. The excavation is progressing underground. And I just sat in on a bunch of meetings. The development is ongoing. And it's like any project. There's a lot of planning that's going involved to make it a success. So it is moving forward. Schedule? I'm not the best person to comment on that. My role is more on the technical side, so I apologize for that. But
All right. Then let's have one more round of applause for our panelists.
Thank you all. I want to say a special thank you to Cham and Pedro, and especially, you know, Cham is in the UK, so he's like 7 hours ahead of us. And look at how fresh he looks. It just and we really appreciate you being here. And Pedro's only an hour ahead, so it's not that big of a deal. But we really love, Pedro stepped in today when one of our other speakers couldn't make it. And so I think it was like 2 o'clock this afternoon. I was having a panic attack, and Pedro said, "Oh yeah, I'll do it, no worries." So we really appreciate that. And now I would like to make a few announcements, just to remind you that there are many other activities going on around the world. Check out the Dark Matter Day Hub at interactions.com, and you'll find stuff from everywhere. I think there are some things going on next week. And also, there is a new Dark Matter podcast that is going to run the first episode on October 31st. It is called Particle Mysteries, The Coldest Case. And the first episode is going to be the spin of the universe. You'll find this link at interactions.org, so please check that out. Now, this Saturday, we are also having Trunk or Treat right here at the Visitor Center, and it is going to be inside. So please come. And last year we had well over 350 kids and parents show up. So please, we would love to have you participate in this. Our next Deep Talks is Thursday, November 9th from 5 to 7 p.m. We're going to be hearing from Katrina Donovan at South Dakota Mines, and she's going to be talking about art and engineering. I think that's great. I used to work at an engineering college, and a lot of what they do is very much art. So I'm very excited to hear about that. And also on November 9th, we have Ask a Scientist from 1 to 3 p.m. right here in the Visitor Center. So please join us for these events. You make all the difference. Thank you so much, and have a great evening and a very safe drive home. Thank you to Gavin as well, and Charles. This has been a great event. So much appreciate it. Give these guys a round of applause. Thank you.